So let's go with one of these other ones, the 13 or the 14. My position on the periodic table did not change. Carbon is still number 6. So it tells me that it's still going to have 2 electrons, 4 in the second shell. But if I think about this radioactive dating, this carbon 14, y'all ever heard of that? Like the C14 dating of relics and archaeology and all that type of stuff? Okay, so if that's a carbon, wait a minute. What's different?
Neutrons.
My neutrons. So in the atom, in the element, in that nucleus, I still have 6 protons, but how many neutrons do I have now?
8.
Now, why is that not organic?
It doesn't occur in nature. It has to be created.
It occurs in nature. They just take it and man plays around with it.
Because it's synthetic.
It would still be natural. It is radioactive. Woohoo. Now, I'm not saying it wouldn't be cool if we were radioactive. Okay? Think about all the light we could generate at night just from ourselves. Electric bills would just go way down. All right? But it's radioactive. Simply because the neutrons changed. When the neutrons change in an element, it is going to make it radioactive. It is now an isotope. Iso means the same, but our numbers have changed. So the carbon 14 versus the carbon 12 would be radioactive. If we were made up of that, we would be radioactive. But wait a minute, are there other radioactive substances that are out there?
Uranium.
Got a whole bunch of them. Some of them occurring naturally, some, a lot of them, man-made. Now, are all of them negative for us as beings? No. Why? Can you think of a way that we may make good use of a radioactive substance?
Some different type of radioactive way they have to treat like cancer.
Okay, the different types of radiographies and stuff like that, and the
Dyes. Like radioactive dyes for like
the
cells
dyes
and
where it'll help us visualize. Okay, what about something like the little, I think they've now made like little radioactive like.
What about the gamma knife? Like Johnson
Yes, that would be radioactive. They've made little like C type things like for the men with prostate cancer that are radioactive that they implant into the area around the prostate to try to kill prostate cancer rather than having to go in and cut, you know, and do all that sort of stuff. So we have learned how to make good use of radioactive materials. And they do exist, all right? They just have a different number of neutrons. So when you change the number of neutrons from what you see on the periodic table, which will be the average, okay? When you change the number of the neutrons, we have generated something radioactive. We definitely make use of these radioactive substances in the clinical aspect, in research. We're using it, for example, treating some cancers that we know about. One of the ways that we can also use it, sterilizing materials that can be used in surgery, tracking the hormone uptake, radioactively labeling the glucose for the PET scan. So there's a lot of things that we use the radioactivity for. In the human body, of course, the goal would be to not have like a lot of that radioactive stuff making us up, but hey, it happens, all right? Because when we are exposed to something radioactive that's already existing in our bodies, the cells of our bodies cannot tell the difference. And that's why they take it in. And it can be destructive to us. But our goal is to not get close to that kind. When we talk about the elements of the human body, these are the common ones. The carbon, the hydrogen, the nitrogen, the oxygen, the phosphorus, the sodium, the magnesium, the zinc, the sulfur, chlorine, calcium, iron, iodine. Ever think about some of these? How would you think of these for the human body?
We think about the potassium, calcium a lot.
Why?
Because the heart works on like potassium, calcium pump. No, sodium cardio.
The sodium, potassium pump, okay? But why would calcium be important? Well, when we hear calcium, immediately things that come to mind, bones and teeth. You're going to need sodium and potassium for everything. You're going to need calcium for proper nerve muscle function. So almost everything. Now, chlorine, for example. What in the world? Okay, the hydrochloric acid that's going to help with breaking substances down. You're going to find other areas where we got chlorine. Well, wait a minute. Time out. Comes to mind when you hear chlorine? Bleach. Okay, that's what I think about, and I'm thinking, whoa, 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 whoa. I'm told you breathe too much of that because it's gas. Once you get near it and it begins to mix with the air, it is a deadly gas. It'll kill you. It's what was used in gas chambers back in World War II. Okay? So, I'm thinking, hey, whoa, why do I have chlorine in my body? It's actually important. What is our source for getting these elements?
Food.
Our food sources. One of the biggest ways that we get these trace elements is the salt. All right? Now, if you think about something such as potassium, what could happen if a person's potassium, like if you're on a call, and but you don't quite know it yet, but their potassium could be too high or too low?
Called dysrhythmias and stuff like that.
We're going to see that with potassiums, sodiums, magnesiums, but really potassium's a bit with calcium, it is going to affect the function of nerve and muscle cells, which can lead to actual stopping of the heart and the lungs and death from something that they're telling me is 0.4% of my human weight. And if it goes too high or too low, I could die. Oh, yeah. Think about that for a minute. Because we're going to carry that with us for everything we're going to talk about. We're going to carry the sodium, the potassium, the calcium. We're going to carry that through every single thing that we talk about. The bonds that get formed are important. When we have one or more elements that can combine, they are going to do so, and they are going to form bonds. The type of bond will determine how strong that molecule will be. When we talk about bonds, when those outer electrons get shared, we go back to my carbon and my hydrogen out here. They're working together with their electrons. In this example right here, they are sharing their electrons. But when one or more elements come together, they do not always share their electrons. Somebody will give up one, somebody will accept one. That type of exchange is going to be ionic bonding. This is when those electrons are not shared equally. Covalent bonding, they're sharing the electrons equally around both elements. When the elements form an ionic bond and somebody gains an electron, loses an electron, they now carry a charge. For example, sodium and chlorine. Sodium is number 11 on the periodic table. The weight is 22, I think, 22. And chlorine is number 17 with the weight, I think, of 35. Now, that is telling me specific information. The biggest information that it's telling me, protons and neutrons in my nucleus and my electrons. So in sodium, in my nucleus, I'm going to have 11 protons and 11 neutrons. That tells me in my first shell, I've got 2 electrons, but I got 9 more that I need to deal with. So in my second shell, 8 of those 9 electrons, I've only got 1 left over. I'm now, with my sodium, in that third shell, which wants to hold up to 8 or 18. Okay? And it's only one electron. Think about that. Is sodium happy? Oh, no. Sodium is so reactive that in a lab setting, it has to be kept under a heavy oil. If it so much as comes into contact with the air, it blows up. Because the water from the air will react with it and make it blow up. I'd pay $10 to see that. Just saying. Now, I got that one electron, not happy, but then here, comes chlorine. So, chlorine comes around. Chlorine is going to have 17 protons. 35 minus 17, 18. Is that 18?
18.
18 neutrons. It's going to tell me that I've got 17 electrons. So in the first, I've got 2. In the second, I've got 8. And in the third, I've got 7. The third one wants to hold up to 8 or 18. So, here I've got chlorine, sodium. Under normal circumstances, they should not meet. All right, but if they do, what is going to happen is chlorine's going to be like, sodium, you've only got one. Sodium's going to be like, chlorine, you need one. And it's going to go, I got it. Here, I got you covered. Take that one that I had and become 8 in your outer shell. We now are a happy ionic bond. In doing this, somebody gave up an electron, somebody gained. That tells me my protons are positive, my electrons are negative, positive, negative. Which did I decrease in number? The negative or the positive?
Negative.
I decreased negative. That makes this more positive. And sodium, therefore, becomes positive. My chlorine, what did I increase more of?
Negative.
The negative. So my chlorine becomes negative.
And they stick together.
And they stick together in what we know, for the most part, as salt. Take a break. Be back at 3:30.